So today what I want to do is I want to quickly wrap up our discussion of renormalization in quantum field theory. And I want to wrap up by describing what's probably one of the most interesting applications of quantum field theory and of the ideas of renormalization. And in particular, I wanted to discuss somewhat generally today the application of renormalization to condensed matter physics. And in particular, what I want to do is describe how some of the ideas that we've been developing over the last week or two can be used to make very interesting, very quantitative predictions for various interesting sort of material systems. So let me just start maybe just by establishing a bit of a language for us to use when we talk about applications of quantum field theory in condensed matter physics. So let's just imagine we have some sort of a material. So let's say that it's a bunch of spins living on a lattice. Okay. So this could, for example, be a nice description of some sort of magnet. And we wish to understand the physics in the very low energy limit, that is to say, in the infrared. And in the infrared, although you have a bunch of spins living on a lattice, you can approximate the spin on a given lattice site, let's call it S of x, by a continuous field. So, for example, if you have a bunch of lattice sites with spins that could be either up or down, then you want to approximate that discrete spin variable with a spin on each lattice site by some field which may, for example, be described by some scalar field phi. And then, if you wanted to think of this as a magnet, say, so that each spin has a little infinitesimal magnetization, then something like the integral of phi would be the total magnetization of the system. So in your various statistical mechanics classes, you're probably familiar with all sorts of interesting spin lattice models. So the Ising model is a famous example where you have spins that can be either up or down and have a nearest neighbor interaction. But of course, there are all sorts of other kinds of Hamiltonians for spin systems that you could write down. And what I'd like to do today is describe a very general approach to the study of these kinds of systems. And really, this is an approach that applies to all sorts of condensed matter systems based on the ideas of the renormalization group. The idea being that we have some fundamental degree of freedom phi. And if we wish to look at the infrared dynamics, then we want to study the theory by describing it in terms of some fixed point in the infrared of the renormalization group flow. So just to be a little bit more specific so that you have some examples that you can think about when we describe this. So here in the picture that I've drawn a spin that can be either up or down. So this would be a good example if you have a spin with some sort of preferred axis. So a spin that can be either up, pointing in the plus z direction or the minus z direction. So you would describe that in the long wavelength limit by one scalar field. Or this would be essentially a spin that's constrained to point in one dimension. If you have a spin which can point in two possible dimensions, which would be some sort of system where you have a preferred plane rather than a preferred axis, you would describe that in terms of two scalars, phi 1 and phi 2. Or if you have isotropic spins, spins that can point in any direction, then you would describe that by three scalar fields, phi 1, phi 2, and phi 3. And in general, one of the models that we often study when we talk about spin systems is known as the ON model. And an ON model is just a model of n scalar fields, phi I, where phi I is an index that runs from 1 up to n, which is invariant under the rotation symmetry. This is not a spatial rotation, but a rotation in field space, where phi I is Oj phi j, where Oj is some matrix that sits inside the group On. If you haven't seen this notation for the group On, that's the n-dimensional orthogonal group, and it has the property that it preserves the invariant inner product delta Ij phi j. If you're not familiar with that group theory language, don't worry. I mean, it's sort of, if you just think about these three examples here, it should be pretty clear. So for example, the O3 model is a model where you have three scalar fields, phi 1, phi 2, and phi 3. That's invariant under the rotations between those fields, where they rotate using the usual rotation group O3, or SU2. But the point is that the low energy physics is determined by the endpoint of some renormalization group flow. And so once you determine the field content and the appropriate symmetries, that is to say, once you decide which fundamental fields you have in your quantum field theory description and the symmetries under which the fields are invariant, you should be able to study the renormalization group flows, look for fixed points under renormalization group flows, and use those to describe the dynamics of these theories. Okay. So, in particular, one of the most interesting things about this way of thinking about condensed matter physics is that the same fixed point can actually describe many sorts of different systems. And this is a notion that sometimes goes under the name of universality. So let me give you an example of this. So later on in this class, we'll study a fixed point at n equals 1. And this fixed point has a name. It's called the Wilson-Fisher fixed point. And this is the fixed point that you would use to describe some system in 3 dimensions where the basic degree of freedom is some scalar field, and there's some additional tuning that has to take place so that the system is at a critical point. That's something that we'll describe in a few minutes. But this is expected to be a generic description of any system which has a critical point and is described by a single scalar field. Okay. So, for example, if you have a liquid and a gas transition, then at the critical point, right near the phase transition, you have essentially a scalar field. The field that determines whether you're in the liquid phase or the gas phase, you could view that as a field, as you could study its properties. Or, for example, if you have what's known as a binary fluid, which is a similar system where you have 2 different fluids, and then you have a field that labels which fluid you're in. This also is a good description of various magnetic systems. So in particular, it's a good description of an antiferromagnet, and so on and so forth. Okay. So you have, as long as you have a description with a system which at low energy has some field content that you can determine or make a good guess for, then you can determine at least some features of the low energy dynamics. Okay. And so, in particular, what we're going to do is we're going to study the fixed points of the renormalization group flow of phi-4 theory and use this to make predictions for various sorts of condensed matter systems. But before I do that, maybe we should step back and just ask very briefly what it is we're trying to predict. So we have a theory with this scalar field phi. And the basic thing that one might be interested in studying, say, in some condensed matter system, is the correlation function between the value of the field as a function of the spatial separation x. So this is the two-point function. And typically, in some sort of statistical mechanics system, the correlation function will, at long distances, fall off exponentially with distance. And the dimensionful parameter that controls how correlation functions fall off with distance is known as the correlation length. It describes the typical distance on which the value of the field will be correlated. So, for example, if you have, say, the Ising model or a spin system, then the correlation length is the typical length at which there's some order 1 correlation between spins at different lattice sites. And if you think about this from a quantum field theory point of view, you immediately know how to think about this correlation length. So if you have a scalar field phi and it's massive, then the Green's function falls off exponentially with distance. And the coefficient in that exponential fall off is the correlation length. So this correlation length sets the mass scale of your scalar field theory. So what I would like to focus on today is not just, so of course this, what I've said so far is just true for free field theories describing some massive scalar field. What I'd like to do is consider a rather special situation where the theory has a tunable parameter and the theory has the property that as you take this tunable parameter to its critical value, so examples of such a tunable parameter would include temperature, or, for example, the doping parameter of some complicated material. And the system has the property that the correlation length diverges at a critical value, say the temperature approaching Tc of this tunable parameter. And when this happens, we say that the system has a phase transition, and in particular, this sort of phase transition, where the correlation length goes to infinity, is called a second-order phase transition. Also sometimes referred to as a critical point. So what we want to do is try and understand general features of these critical points where the correlation length diverges. So let's just, for the sake of definiteness, imagine that our tunable parameter is the temperature. So we're studying some magnetic material, say a ferromagnet, and as you dial the temperature, as you lower the temperature, so at very high temperature, the spins are all disordered, and the correlations fall off exponentially, where the correlation length is determined by the temperature. And then as you approach a critical value, the correlation length diverges. What does that mean? That means that suddenly all of your little spins, which had been disordered and unaligned, are suddenly becoming aligned. And so that means the system is entering a magnetic phase, whereas previously, or an ordered phase, whereas previously it was in a disordered phase. So typically, so the correlation length diverges. And so let's let our tunable parameter, let's call it T. So in the case of that ferromagnet, we can define a dimensionless tunable parameter. And let's ask what happens as we approach the critical point. Then, as you approach the critical point, the correlation length is going to diverge. And so it will diverge typically with some power of T, with a power that I'm going to call mu. And at the critical point, the correlations are no longer exponential, but because the correlation length has gone to infinity, we no longer have a dimensionful scale in the problem. So the correlations are no longer going to be fall off exponentially, but they have to fall off as a power. So typically, they'll fall off like 1 over x to some power. And so I'll call that power d minus 2 plus eta, where eta is a number that we're going to try and predict. So these two parameters, nu and eta, are parameters that characterize the behavior of the system near its critical point, and they're typically called critical exponents. And there are all sorts of other critical exponents we could define. So for example, you could study the specific heat of the system, which measures how much energy you have to pump into the system in order to change its temperature. That will also have some critical behavior that's governed by some exponent. And if you look, for example, in Peskin and Schroeder, or in Zinn-Justin, or in any number of textbooks, you'll see a whole list of different sorts of critical exponents that you could write down. For the sake of simplicity, I'm just going to focus on these two critical exponents. So what I would like to do then is describe how we're going to compute these using a renormalization group approach to quantum field theory. So the first thing that we need to do is we need to think about exactly how it is we want to describe our material using quantum field theory. So the quantum field theory description of our material is almost, but not quite, identical to the sorts of quantum field theories that we've been studying so far in this course. So far we've been studying Lorentz invariant quantum field theories consistent with the symmetry of special relativity. Of course, for some material, Lorentz invariance isn't going to be particularly useful. Instead, the system is only going to be invariant under spatial rotations. And in the quantum field theory description, we therefore don't have the full Lorentz symmetry, but we only have the spatial rotation symmetry. And in this quantum field theory description, the dynamics of the system is such that we minimize not an energy, but the free energy of the system, which we can regard as a functional of our degree of freedom phi, just as we would in a quantum field theory. And we then wish to imagine expanding this around for small values of phi to get a perturbative expansion for the dynamics of the system, just as we do in all of the quantum field theories we've studied so far. So, for example, the Lagrangian would have a kinetic term. Now here, this would just be a gradient term, so a spatial derivative term, and some potential term, which if you expand order by order in phi, you would expect to have, say, a mass term That goes like a phi squared. And then, well, if you have a phi to minus phi symmetry, such as with the spin system that I described to you earlier, because you can just use a symmetry under flipping the spins, you wouldn't get a phi cubed term. So the next term that you would get would be phi fourth, and then so on and so forth. And here D is the number of spatial dimensions. Okay. So the first thing that I want to do before using renormalization group flow or anything like that is let's just imagine that our system has the property that B is very small, so that we can treat it just using perturbative quantum field theory. So this description of a phase transition, a critical point, using perturbative quantum field theory is known as Landau theory, or the Landau description of this phase transition. So in this case, it's very easy to determine these two critical exponents just using what we know about free field theory. So, for example, the Green's function. So Landau theory is the theory where B is very small. So the Green's function, well, in position space, it's just the free Green's function, which we could write as the Fourier transform of the momentum space Green's function, okay, which I've written here. So A is playing the role of the mass squared, and this is a Euclidean momentum k, corresponding to the fact that I just have spatial directions, no time direction. And, well, this is a Fourier transform that you've done already in this class. And the answer is just, well, you know it has to have a 1 over r, just for dimensional reasons, and then an e to the minus r over, say, some correlation length that goes like 1 over the square root of a. Okay. And we then want to use this to make some sort of prediction for our critical exponent nu. Remember, nu is the critical exponent that told us how the correlation length diverged as we approached a critical point. So in order to understand that, we need to think a little bit more clearly about exactly how this phase transition is being described in the quantum field theory language. So in particular, we want to study a phase transition where the correlation length diverges as t goes to 0. And the correlation length is going to diverge only when that parameter a goes to 0. So what we do is we Taylor expand near a t is equal to 0. And a will have a term that's linear in t plus higher order terms that can be neglected very near the phase transition. So if you want to think about it, what we have here is a Lagrangian where you have some potential for phi. And what the potential looks like, so here, if we just graphed v of phi, is that for t bigger than 0, so if you're just above the phase transition, the potential looks something like that. Whereas for t less than 0, when you're on the other side of the phase transition, the potential looks something like that. And so the way that the phase transition occurs as t goes from slightly positive to slightly negative is that the ground state of the theory, the lowest energy state, or the state with lowest free energy in this case, would move from being at phi equals to 0 when t is greater than 0, so that would mean that the magnetization is equal to 0, to phi being non-zero when you're on the other side of the phase transition. So this describes a system where the spins are disordered in the high temperature phase and become ordered, and the system becomes magnetized in the low temperature phase. So you can see from this that the correlation length will go like t to the minus 1/2, just from this formula here, expanding A at linear order in t. And the Green's function will be just that for a free field. So it'll go like 1, well, it goes like 1 over k squared in momentum space, which is 1 over x to the d minus 2 in position space. And so the critical exponents, using the Landau theory, are 1/2 and 0. Okay. So this is our first prediction of quantum field theory for the critical exponents of some system near its critical point. Okay, so that was reasonably straightforward. It was just free quantum field theory. What I now want to do is consider a slightly more interesting case where we have a quantum field theory, a system that's described by a critical point that's non-trivial and interacting in the infrared. Before I do that, let me see if there are any questions. Yes?
So the temperature also inside A is a function.
Yeah, that's right. So what you imagine is that, you know, T is some tunable parameter. Okay, so it could be the temperature. So this would be a very familiar example where if you have a system that's magnetic, undergoes a magnetic phase transition at low temperature, as you lower the temperature, spins become more and more correlated. You know, at very high temperature, everything's disordered. It's very hard for spins to become correlated. And so you imagine that as you lower the temperature, the effective mass of the quantum field theory gets lower. Right?
B doesn't depend on
Theta.
B.
Well, B in principle could as well. Okay. Yeah. But yeah. I mean B, but you know, it'll at near t equals 0, it will be some constant B naught plus something linear in t, and so on and so forth. But at leading order near t equals 0, it'll just be a constant. And you can see, of course, clearly this system, this description of the phase transition will only work if B has positive sign, right? Any questions? Have you guys seen this before? This is new, mostly, more or less. You don't study this in your StatMac or classes? You do this, but nobody takes StatMac. One person takes it. Okay, good. Okay, so now what about what happens if the IR fixed point is non-trivial? Okay. So what if we have a theory where in the infrared you have not a free theory but an interacting theory? So we're studying a scalar field theory, and we expect that at long wavelength, the only operators that should be relevant are the operators that are relevant, namely those whose coupling constants have positive mass dimension. Now, of course, we're not usually interested in magnets in a world with 4 spatial dimensions. So that means that in 4 dimensions, as we've learned before, the lambda coupling in lambda phi to the 4 is dimensionless. But in less than 4 dimensions, it's dimension full. It has positive mass dimension, so it becomes more important in the infrared. So in particular, I'll remind you that the coupling constant lambda has dimension 4 minus d in d dimensions. And, well, the mass squared coupling always has dimension 2. That's easy to see. And so what we want to do now is try and understand what sorts of non-trivial infrared fixed points we could have in these theories and use these to make predictions for these critical exponents. So the first thing that I want to do is I want to make our lives a little simpler. So I want to study the renormalization group flow of this theory. But I want to make our lives a little simpler because the fact that the mass m squared and the coupling constant lambda are dimension full rather than dimension less makes some of the formulas a little bit more complicated. So what I want to do is make things a little bit simpler. So I want to pull out factors of the renormalization group scale, capital M, so that I now have two couplings that I've called rho sub m and lambda, which are now dimensionless. And the point is that the two-point function, g of x, is no longer the free two-point function, so it's not 1 over x to the d minus 2, but rather it's some non-trivial function, but it's constrained by the fact that it obeys the Kalin-Zemanzik equation. So let me just remind you what that was. The Kalin-Zemanzik equation tells you that as you vary the renormalization scale, okay, the energy scale at which we're defining our couplings, then the Green's function is not invariant, but it transforms. Okay? So in the case of phi to the 4 coupling, we had a beta function that we called beta lambda. And the Green's function, the logarithmic derivative with respect to our g scale, was given by the beta function times the derivative with respect to coupling of the Green's function. We also had an anomalous dimension term that I called gamma. That just reflects the fact that our fields have some dimension. So this gamma phi was just the wave function renormalization of the fields as you change the renormalization scale. And now here I'm studying a theory with two dimensionless couplings, and so there'll be two beta functions. So there'll be a beta m, d by d rho m, in addition to the beta lambda, d by d lambda. And here we're regarding this two-point function. So what is it? Well, it's a function of the renormalization group scale. It's a function of the couplings. And it's a function of x. Or if you like, you could call it a function of p if you want to work in momentum space. And just to remind you, the beta function is defined to be the change in the coupling with respect to renormalization group scale. So here you imagine fixing the bare parameters of the theory, integrating out degrees of freedom down to some scale capital M, and as you integrate to lower and lower degrees of freedom, the effective coupling constant describing that low energy theory is going to change. Okay? And same for the coupling constant rho. And finally, the anomalous dimension is describing the change in the wave function renormalization for the scalar field phi. And actually, just sort of for convention, we include a factor of z there. So this reflects the fact that if you start with a bare field phi naught defined in terms of some UV theory, then you write the low energy effective theory in terms of some renormalized field phi, and the renormalization constant is going to be a function of the renormalization scale. It depends on how many of those degrees of freedom between m and the UV you have integrated out. And these are all things that you know how to compute, at least in principle. Okay, so the last two classes we computed them in some of these beta functions in two different ways. Basically, you can either compute them explicitly by integrating out some fields, or you can compute them by looking at the counter terms and the logarithmic divergences in the counter terms. The coefficients of those logarithmic divergences give you the beta functions. So we did that last class, I believe, using the Kalin-Zemanzik equation, and I think you're doing it again on your problem set due on Friday. Okay, but the question really is, given these beta functions and these anomalous dimensions, how can we use this to make some sort of predictions for these critical exponents? So the basic point is the following. So we've decided to look at near a critical point. And near a critical point, we've decided to tune everything so that the correlation length diverges. And so that means that rho m, the mass scale, which determines the effective mass scale of your low energy theory, will be very small. Now, we could go exactly at the fixed point where it's going to be 0, but generically, you at the very least hope that you have a system which is described at least approximately by the fixed point, where rho m is going to be very, very small. And this is so that the correlation length is very, very large. And moreover, we're looking for one where the theory is non-trivial, it's interacting, and so that the coupling constant is not equal to 0. So in fact, last time we already gathered all of the ingredients to discover such a fixed point of the renormalization group flow. So in particular, last time, and in fact, I guess we did this computation 2 different ways in both of the last different classes. We computed the beta function for lambda phi to the 4th theory, and it was 3 over 16 pi squared times lambda squared plus order lambda to the 4th. So this was the change of the coupling constant with respect to our g scale. And last time we did our computation for theories in 4 dimensions, where lambda was dimensionless. Here we're looking at theories in less than 4 dimensions, where lambda is dimension full. And it turns out that the calculation of the beta function is identical in lower dimensions. So all of the computations that I did last class go through. The only difference is that I've pulled out a factor of m here. I've pulled out a factor of m to the 4 minus d here. So you have to correct the beta function to take that into account, because as you change m, this coupling constant right here will actually change as you change m, just because I've pulled out that factor of m to the 4 minus d. So here in less than 4 dimensions, the beta function is just given exactly by what I wrote before, except that it has a term linear in lambda, which reflects the fact that lambda, even at very small values of lambda, the coupling constant will change with normalization scale, just because it's dimension-full rather than dimensionless. I mean, that's an easy way of remembering this, is that the leading term in a beta function is just given by the dimension of the operator. So remember, the beta function is defined to be the change of the coupling constant with energy if lambda has dimension d minus 4, or 4 minus d. Well, that's reflected in that first term in the beta function. And so the fixed point that we're looking for is the one where rho m is exactly equal to 0, so that the theory is massless, and the beta function has a fixed point, so that the coupling constant will approach some fixed value in the infrared. And you can see here that this will happen only when the dimension is less than 4, so that this coefficient here is positive, so that you can have a cancellation between a negative and a positive term. And this will happen at a finite value of the coupling constant, which is just found by setting this beta function equal to 0, which is given by 16 pi squared over 3 times 4 minus d. So one of the things to notice about this formula is that lambda is not small at this fixed point. Okay? So this is not a weakly coupled fixed point unless d is very close to 4. Now, 3 is not particularly close to 4, so the value of lambda at this fixed point is not small. So that means that naively, so that means that you can't use perturbation theory to study this fixed point, at least not standard perturbation theory. Now, the approach that Wilson and Fisher used, which is a, well, you know, it's not particularly well justified, but it turns out to be very close to correct. It turns out to give you very good results. Is they just said, well, let's treat d minus 4 as a small parameter. We'll call it epsilon. That's what we've been calling it so far. But we'll imagine that epsilon is very small. And when epsilon is very small, lambda at the fixed point is very, very small. It's very close to 0. So you can use perturbative techniques. You can use Feynman diagrams. You can use all of that stuff. And so they just said, well, let's compute for very small values of epsilon. And then at the end of the day, set epsilon equals to 1 and hope that we get a good approximation to the right answer. Okay. And it turns out that that hope was justified. Okay. As we'll see, when you do this, it turns out that you get answers that are within, you know, for the critical exponents that we'll be talking about today, within a few percent of the correct value. But you should always remember that this is just, you know, a sort of cheap trick, okay? And there's no guarantee that things like this will work. And so one of the sort of most important open problems, I would say, in quantum field theory is to develop some other new angle of attack on this non-trivial interacting fixed point in 3 dimensions. So, yeah, and so I think there's actually a lot of very interesting work being done on this. You know, I mean, I think it's an important lesson that you can easily be misled when you start computing Feynman diagrams to think that quantum field theories are nice and easy to understand. But there's no reason why a physical system that you're interested in should be given by a weakly coupled field theory. And I think these, you know, you know, as we'll see, the Wilson-Fisher fixed points are incredibly important and describe all sorts of systems, and they're just not weakly coupled field theories. Okay? So if you try and, you know, so people study these using numerical simulations, using what's called lattice quantum field theory. People study these using other sorts of techniques. There's all sorts of things that people can use, but it's a very difficult and I think, you know, open problem. I think the exact. So for example, it is an open problem whether you can find exact analytic expressions for the critical exponents of the Wilson-Fisher fixed point. What I'll do is I'll tell you how to describe approximate expressions, assuming that 3 is close to 4. Yes?
Is it actually a lot of class QFT being applied to this analysis? Because I mostly hear about the
Absolutely. Absolutely. Yeah. Yeah. So right now, the most accurate descriptions of the system come from lattice. Good. Okay. So what I would like to do now, however, is just assume that 3 is close to 4 and tell you how it is we can now make predictions for these critical exponents. So what we want to do is determine the 2-point function at this fixed point. And we want to use the fact that the 2-point function, regarded as a function of the renormalization group scale, the couplings, and I guess I'll call it, let's work in momentum space. We want to use the fact that this solves the Kalin-Zemansek equation. So the first thing that we can do is we can use the fact that because rho and lambda here are dimensionless couplings, just by dimensional analysis, this can be written as 1 over p squared times some function of p squared over m squared. And so that means that when we determined, if you studied the change of this with respect to the renormalization scale m, then that is completely equivalent to studying the change with respect to the momentum p. So the Kalin-Zemansek equation, which started life as an equation where we studied the derivative with respect to the renormalization group scale, now becomes a differential equation for, a differential equation. So here, let's just remind ourselves of the Kalin-Zemansek equation. So here is the Kalin-Zemansek equation, which told us how the Green's function depend on RG scale. Now it turns into an equation which tells us how the Green's function depends on the momentum scale, the momentum p. So it tells us that p, d by dp, well, you get a plus 2 coming from this term here. And then you get a plus beta lambda, d by d lambda, plus beta m, d by d rho m. And then you have the anomalous dimensions. Okay, and there was 2, because it's a 2-point function, of g2 is equal to 0. So, for example, if all of the beta functions are equal to 0, and if the anomalous dimension is equal to 0, the solution is just g is equal to 1, and you get the free field propagator. More generally, what we want to do is now understand how to write down the solution of this when the coupling constants are non-zero. And indeed, they are effectively scale-dependent because they change with renormalization group flow. So we need to write down the solution to this equation. So here, this is now just a question in differential equations. So here, beta, all of the betas, and the anomalous dimensions are functions only of the couplings, so functions of rho m and lambda. And it's, I don't know if you studied this in your differential equations class, but it's a reasonably straightforward exercise to at least implicitly write down the solutions of this differential equation. And this is done using what's known as the method of characteristics. So the idea, so let's just consider a simple case, just to make the notation simpler. So what we want to do is take p d by dp plus beta lambda d by d lambda plus 2 times 1. I got a minus sign wrong. Okay, I'm sorry, I got a minus sign wrong. I pulled out a minus sign here. So let's see, these are all minus signs here. Sorry about that. So it's beta p d by dp minus beta d by d lambda plus 2 times 1 minus gamma of g2 is equal to 0. Okay. So I'm just neglecting that rho term for the time being, just to make the notation a little simpler. So in order to solve this equation, the first thing that we do is think about the coupling and how it changes with scale. So g is a function here of both p and lambda. But we know that as you change p, the effective coupling will change. So let's define a new effective coupling lambda bar that's a function of p and lambda, which has the property that p d by dp of lambda bar is equal to beta of lambda bar. So that's just the beta function. And at least implicitly, it's easy enough to solve. If you just think of this as a d by d log p, and then just to make the dimensions work out, write that as log p over m. So we want to define lambda bar as the solution of this equation. And we'll just take the boundary conditions so that lambda bar at the renormalization scale m, the scale of the theory, that should just be equal to lambda. So that's just our boundary condition. So lambda bar is the effective coupling that tells us how lambda changes as we go deeper into the infrared, given the value of the coupling at the renormalization scale m. The solution is given, well, this actually is something that we did before. So lambda bar is then found by, you just multiply both sides, you look at this equation here, multiply both sides by d log p, divide by beta, and integrate, and you get the integral d lambda prime over beta of lambda prime is equal to the integral d log p prime over m, where you integrate from m up to p. So that reflects the fact that we're imposing this initial boundary condition here. And the point is that the derivative of lambda bar with respect to log p is just equal to the beta function times the derivative with respect to lambda. And the point is that this differential operator here is the same as this differential operator here. So if you forgot about this second term here for a second, if you just forgot about that second term, then the solution, so this is a function of m, p, and lambda, would just be that g2 is some arbitrary function, I'll call it curly g, that's what my curly g's look like, of lambda bar of p and lambda. Is that clear? Now we just need to take into account this term here. Well, that's easy to do. There you just have to integrate so that you have a p d by dp that has to integrate up to give you this term. So you just have to multiply this times the exponential of 2 times the integral d log p over m from m up to p of 1 minus gamma. And this is gamma evaluated at lambda bar. Or if you want to write this a little bit more closely to the expression for free field theory, we can pull out, you can do this part of the integral explicitly, and you get a 1 over p squared times some function of lambda bar times the exponential of twice the integral of gamma. Sorry, this is the integral d log p. Good. Oh, and I guess I made there's a minus sign here, which is really, yeah, which is because there was a plus sign here. Good. Okay. So, I mean, this is just a little lesson in differential equations. If you haven't seen this before, I might have gone through it a little quickly, but it's easy enough to verify. I encourage you to work it all out on your own. The important point, I mean, the thing that you really want to take home about this expression is the following. So far in this class, we've talked about scattering amplitudes, and we've talked about how do you compute correlation functions using Feynman rules. And so you probably want to think, in your head, you think about computing using Feynman diagrams to get a Green's function, which is given by its free value, plus terms that are order lambda squared, order lambda fourth, and so on and so forth, computed using Feynman diagrams. But now that you've started thinking about renormalization flows, you have to ask the question, at what renormalization group scale are we defining that coupling lambda? And the idea is that this expression that we've written for the Green's function is one where if you study the Green's function at momentum scale p, you define it completely in terms of the couplings that appear that are relevant for the momentum scale p. So if you're studying a low energy scattering amplitude, you use the coupling constant of the low energy theory. You study the high energy theory, you use the coupling a high momentum 2-point function, and you're using the coupling constants of the high energy theory. And so really what we've done is we've taken the usual perturbative description of the Green's function, and we sort of resummed a lot of the terms in the perturbation theory in order to write it in a way that looks sort of much more consistent with the way that we think about couplings changing with energy scale. So any questions on this so far? So what I want to do now is just use this to make some statements about the Wilson-Fisher fixed point. So at the fixed point that we're interested in, lambda is just equal to a constant, so it's independent of p. And so that means that gamma is just given by a constant. And so you can do this integral here. So the integral d log p, so of gamma, what is that? Well, that's just the log 2 gamma times the log of p, otherwise known as the log of p to the 2 gamma. So when you exponentiate it, what you find is that the 2-point function, you have that I over p squared out front, but you now have a correction term, which is equal to 2 gamma. So you get 1 over p squared minus 2 gamma. So this is the 2-point function in momentum space. So in position space, we need to do the Fourier transform. Okay, that's just dimensional analysis. P goes like 1 over x. We have a d-dimensional integral there. So this goes like 1 over x to the d minus 2. That's just the d dp, the integration measure, and this p squared, plus 2 times the anomalous dimension. So that means we now have our first prediction for a critical exponent. The critical exponent that I call eta is just the anomalous dimension of the field phi at the fixed point. So this is something that you could now just go ahead and compute using quantum field theory. It's not particularly difficult. It's not particularly easy either. You know, I didn't do it last class because it's actually in phi 4 theory, it's a 2-loop computation. instead of a one-loop computation. I think in Yukawa theory it's one loop, so I think you'll find an anomalous dimension for phi in the problem set that you'll do Friday, I think. So, for example, you're going to compute, if you had some system whose critical point was governed by Yukawa theory instead of by phi-4 theory, then you would be computing, one of the things you're computing on Friday is this critical exponent. Okay. How about the other critical exponent? So in order to understand the other critical exponent, we need to think a little bit more carefully about what we're doing. By the way, are there any questions before I continue? So remember, the critical exponent that I called nu is determined by thinking about how it is you approach this critical point. So as you approach the critical point, the correlation length is supposed to diverge. And from this point of view, from the renormalization group point of view, how should we think about this correlation length? Well, you have a correlation length that's not infinity when you're not exactly at the critical point. So rho m is not exactly 0, but rather it's almost 0. And if rho m is almost 0, then that means that you should study the effective value of rho m at some longer wavelength scale. So this will obey. So the renormalization, the change of the effective mass with respect to our g scale is again given by a beta function equation. So it's beta m and at leading order, this is going to be proportional to rho. So remember that if you were working just in a free field, if you were working in a free field theory, this would just be 2 times rho, because it would be the dimension of the mass term. So more generally, it's going to be some constant times rho. So just see if I... So typically, it'll be some constant times rho. So let's just call it, I don't know, Cm times rho. And so that means that if you fix rho m at the renormalization scale capital M, then at some lower energy scale, the coupling rho bar, well, you just solve this differential equation. And the solution is so rho m bar is equal to rho m, the value of the coupling at the renormalization scale capital M, times whatever powers of the momentum you need in order to solve that equation. So what this means is that if you started the theory where rho m is very small, and then you go to lower and lower energies, you just go farther and farther into the infrared, you study the theory at longer and longer distances, the value of rho is effectively getting larger. Okay. That constant is negative, by the way, right? Reflecting the fact that the coupling is getting larger in the infrared. So what that means is that the correlation length is effectively the scale when this coupling becomes of order 1. The correlation length is given by rho m is equal to 1. So at that length scale, or to say that a little more clearly, the correlation length is 1 over the value of p, so it's the length scale, where rho m of p is equal to 1. So using this equation here, hopefully if I haven't messed anything up, so rho m bar is equal to 1. So that means that the correlation length goes like rho m to the 1 over Cm, whatever that constant is. Or, since remember that rho m, so rho m is the parameter that I called A, so just to remind you, rho m is just this parameter that I called A here, which is linear in t. So this goes like t to the 1 over c. So that means that the critical exponent is 1 over c, where c is the leading coefficient in the beta function at the critical point. So sometimes people give a slightly different name to this. Sometimes people call this 1 over, so in the, yeah, okay. Let me come to that in just a second. So if you know the beta function coefficients and the anomalous dimensions, you can now compute these these coefficients, eta and mu. So just as a sanity check, let's just check that we understand this for free quantum field theory. So for example, in free quantum field theory, what is the anomalous dimension? Well, the anomalous dimension was the change in the wave function normalization with m. But in a free theory, there is no wave function normalization, so z is equal to 1. So this is 0. So that, according to this dictionary, the critical coefficient eta is equal to 0. Likewise, in a free theory, the change of the parameter rho m is only governed by the fact that we pulled out an overall factor of the normalization scale m squared to make that coupling constant dimensionless. And so that gives you just a 2. So that tells you that nu is equal to 1/2. And indeed, these are exactly what we had in the Landau theory. So this dictionary that we've written down is exactly what you would expect, gives you exactly what we would expect in free field theory, but we now know how to use it, at least in principle, for interacting fixed points. So let me just now, I'll need to get going in a second, but let me just now tell you some comparisons with experiments. So, for example, if you take the parameter that we called nu, then in the Landau theory, this is equal to 1/2. In the Wilson-Fisher fixed point, you can actually compute this critical exponent. It's a little subtle, so the way that people actually do this computation is they work at as high order in perturbation theory as they can, and then they try and resum that perturbation series or try and use some, if you know a bunch of terms in a perturbation series, you can try and make some guesses as to what that perturbation series will converge to. Okay? So people use these resummation techniques. They get an answer of a little over 0.6. And the experimental answer depends on exactly what systems you're studying. But for example, in liquid-gas phase transitions, you get about 0.625. For an antiferromagnet, you get about 0.65. Okay. So clearly, this is a much better description of the system. The Wilson-Fisher fixed point is a much better description than free quantum field theory. Similarly, for this parameter eta, that's equal to 0 in the Landau theory, and a little bigger than 0 at the Wilson-Fisher fixed point. And in the liquid gas, you know, it's about 0.016, and in the antiferromagnet, it's about 0.04. And then if you look at various other sorts of systems, you can find other comparisons. So for example, if you look in Peskin and Schroeder, there's a big table where he looks at the ON models, not just the single scalar field, but many scalar fields. And so, for example, the O3 models, which would be relevant if you had a spin that was allowed to move in 3 dimensions, are very good descriptions of all sorts of ferromagnets. If you didn't know about the renormalization group description and the Wilson-Fisher fixed point, you would have no reason to suspect that all different sorts of ferromagnets that you could study would have the exact same critical exponents, but they all do, and they all are more or less given by this non-trivial fixed point. So this sort of concludes the portion of the course where we talk about renormalization. Starting next class, we're going to be moving on to Yang-Mills theory and gauge theories. So I think it's time for me to go. It's 3:45, but let me just see if there's 1 or 2 quick questions. No questions? Okay, I will see you on Thursday.